Hi, my name's Layla and I'm in fourth grade. My question is, if a comet hit Earth, how deadly would it be?
Well, if a large comet hit the Earth, it would be a very bad day for all of us. The damage could be, depending on the size of the comet, either local damage or global damage. A smaller comet, say the size of Hartley 2, would create a huge crater and maybe disrupt the climate of the Earth for years, while a much larger comet could cause a mass extinction like the one that killed off the dinosaurs 65 million years ago. The good news is that these things happen very rarely.
Hello, my name is Enrique Gomez from Western Carolina University, and in this podcast, I'm going to be talking about cosmic collisions in small bodies and planets. The questions that we're going to answer today are the following. We're going to be talking about whether we have ever witnessed a major impact. Did an impact really kill the dinosaurs? Is the impact threat to Earth a real danger or just media hype? How do other planets affect impact rates and life on Earth? So have we ever witnessed a major impact? And the short answer for this is yes. So the best example of this is the impact of the comet Schumacher-Levy in 1994. This is a comet that came close enough to Jupiter that it got broken up into many smaller pieces. And in this image taken before the collision, this comet had broken up in what's called a string of pearls. Now, after that comet made its way through the inner part of the solar system, it happened to have been close enough to Jupiter that it made direct impact. So in this picture, SL9, also the other name for Schumacher-Levy, caused a string of violent impacts in Jupiter over several days in 1994. And this was a strong reminder that those catastrophic collisions in objects of the solar system still happen, and they are not limited to the early history of the solar system. The tidal forces that tore this comet apart in a previous encounter with Jupiter. In this diagram, we see what the comet's original trajectory would have been had it not come close enough to Jupiter, and what its trajectory eventually became, so that it eventually impacted Jupiter itself. In this animation, we have a comet-like object in the blue under the gravitational effect of Jupiter. In this particular configuration, what we see is that the orbit of the comet is also going to be distorted. After a few passes, we see that that comet has to been altered so much that it has crashed into Jupiter. In this animation, we see how fragments of comet Schumacher-Levy 9 are impacting Jupiter in the dark side. This happened during 1994, and it took several hours before the impact sides began to appear. And this happened over a period of several days, leaving dark marks of ejecta on the upper atmosphere of Jupiter. This is an image taken from Jupiter in one of the first impacts of Jupiter, one of the first impacts. This is an impact of a plume that emerged just below just above the limb of Jupiter. Unfortunately, from our point of view, we couldn't see the impact directly. Instead, what we got to see is this plume of really hot material that got ejected and eventually fell back into Jupiter. The energy release here came to be above 6 million megatons of TNT, or about 600 times the world's nuclear arsenal. This is a series of photographs taken from top to bottom of what happened over the subsequent days. So some of the first impact caused a lot of dark circles, dark material, which we think is a mixture of gases that got stirred up from the center and got burned up by the impact. Now, as more strings impacted, or more parts of Sumeracco Lake impacted, you had along the same latitude lots and lots of little pot marks. Many of these impact marks were visible from small telescopes on Earth. It's still a mystery exactly why is it that we have dark materials over there. It seems like we have the signature of sulfur compounds and lots of burned up carbon compounds, but still is something that even more than a decade after the impacts happen, we don't still have a full understanding of this. So these are more images of the impact side, and we see from different frequencies corresponding to the UV, the violet, the blue, and the red, and say images from methane over there. These various frequencies allow us to have an estimate of the temperature of the plume, and the size along with the temperature let us know how much energy was released. Now, it has been a mystery for a long time before this Jupiter impact occurred as to why you see features like this on Jupiter's moon Callisto. And that is that we have shown a string of comets. Turns out that in prior history, comets probably were disrupted often enough, producing a string of pearls, and hence you will have an impact feature or a crater chain like we have in the moons of Jupiter. Now, more than a decade passed before there was a suspicion that an impact happened rather recently within the last year or so. So an amateur astronomer in Australia took this image of Jupiter showing a dark spot, which is consistent from we know in the past from a dark feature from an impact. And zooming in, this is a picture taken by the wide field camera for the Hubble Space Telescope, that this impact size with its dark plume is about twice the size of the Earth, a very substantial effect. Now, we see other impacts in the solar system. So, for instance, the instrument Linear happened to detect the following object, which is not quite a comet, but instead, we believe, is two asteroids that have recently collided with each other and that has left a trail of debris behind it. Now, this is consistent with our ideas in the solar system that impacts of asteroids help make larger and larger objects. So at this point, you should be sufficiently worried that something could happen closer to Earth or maybe to Earth itself. We know of several impact features on the surface of the Earth, and we're pretty sure that they are not, say, volcanic elements. The most famous one of this case is Barringer Crater in Arizona, which is just a few miles south of the south rim of the Grand Canyon. So just to give you some perspective, this is about 1 kilometer wide or less than a mile wide. Okay, so this is going to be a visitor center, and if you ever have a chance to visit the Grand Canyon, it is worthwhile to come and actually see this up close for yourself. This is an image taken from the rim from the visitor center. Earlier in the history, Mr. Barringer, when he made an argument that this was an impact site, suspected in the center of the crater there would be lots and lots of iron from the impact. Now we know that this object, whatever it costed, even if it were made of iron, probably all that iron melted and vaporized before it made an impact on the surface of the Earth. Now, we think that this happened about 500,000 years ago, and that the object that produced it was about 50 meters across. We know that there are many impact features around the Earth, about more than a dozen or so. For instance, this is a recent discovery from 2010 of an area that from the southern Congo that got deforested to reveal an impact creature. So we know that there are several of these things around that. It does happen here on Earth. It's just that the Earth, through various processes of erosion, has eliminated most of the cases of cratering compared to other bodies in the solar system. Now, another very famous event was the Tunguska event that happened in the earlier part of the 1900s. So this event happened in Tunguska, Siberia, around June 30, 1908. Now, we only have the effects of the local area in Siberia, along with several witnesses who reported something very bright and very massive that caused such a strong wind that people got knocked off to the ground. We think that the object that produced this was about a 40-meter large object that disintegrated and exploded in the atmosphere, causing a shock wave that destroyed most of the trees surrounding the area and even knocked them out like matchsticks, pointing roughly in the direction of where the impact center would be. Now, one of the bigger mysteries is how come this object didn't actually produce an impact crater like other objects? We have done lots of modeling, scientists have done lots of modeling of the effects of an object entering an atmosphere. We know, for instance, that such objects come at 40 kilometers per second, so they are supersonic. And what happens is that it produces a turbulent wake and a wake shock, so that it will produce a large enough shock to be felt in the ground and even knock buildings and trees. Now, in front of the object as it comes in, there is an accumulation of gas that is compressed because it doesn't have enough time to expand on the sides. So if you have an object coming in space with lots of internal cavities, as it comes in fast enough, the atmosphere in front of it doesn't have enough time to move out of the way, and it just accumulates, creating tremendous temperature and tremendous pressure on the object. Eventually, the pressure is enough that the object starts to be compressed, and it may even liquefy entirely. So whenever you have gas that is compressed and raised to a high temperature, eventually you're going to produce a shock wave that travels faster than the speed of sound. Now, this is the very definition of a shock wave of an explosion. So you could think of an object that as it comes in, of producing an explosion at some point as it enters the atmosphere. Now, the vast majority of objects don't actually make it as a solid object to the ground. They just vaporize, but a handful are large enough that they actually bring some debris right to the ground. So this is a painting rendition of what happened in Tunguska. This is a painting by Don Davis. So we think that an object came in the upper atmosphere, and at some point the gas had enough pressure and was hot enough to actually cause a detonation that completely broke the object apart, producing a large fireball and a set of shock waves that knocked out many of the trees and producing a tremendous amount of forest fires. This debris was also expanded around the world, and there are reports that within a few days, the atmosphere, the gas on the upper atmosphere was bright enough at night that someone could read the newspaper in London during midnight. What this suggests is that these events happen often enough to actually be of concern and actually shape many of the things and the history of the solar system. So for instance, the Earth is unusual because it has a moon which is substantially larger compared to its side, and this is rather rare in the solar system. We believe that in the early history of the solar system, the early history of Earth, there was a giant impact where you have an object about the size of Mars impacting the Earth. Some of that debris was left in orbit around the Earth, did not escape onto outer space, and that debris essentially built up the moon as we know it today. Now, a little bit later on in the history of the solar system, you have several extinction events. Could they be associated with impacts? And for instance, the popular idea that the impact from a large body killed the dinosaurs. Now, mass extinctions are a regular feature on Earth. For instance, they are defined by large dips in the total species diversity of the fossil record. Certain mass extinction events like the Lair Permian were so tremendous in their effect of diversity that not only species but whole families of animals completely disappeared from the fossil record. The most recent one was happened around 65 million years ago, ending the reign of the dinosaurs, and we know this from the geologic record. And the question is, was it caused by an impact, and how would this have happened? Now, before the 1980s, the thought was that there must have been a massive volcanism event that essentially polluted the atmosphere to such a level that trees and other plant matter stopped growing, and the dinosaurs, since they are dependent on plant matter, at least at the lower end of the ecosystem, essentially perished. Now, when you look at the fossil record, right up to the geologic record, right up to the what's called the KT event, where the dinosaurs disappeared, you see something very curious. So, for instance, the lower layers here correspond to the reign of the dinosaurs, and then you have the upper layers in this cross section of the geologic record corresponding to the KT event, or the time in which the dinosaurs disappeared. You see no fossil records around these layers. Now, the point in between, you have a layer containing a lot of iridium, and iridium is unusual on the surface of the Earth. It's something that you expect to see at the lower levels and you would of the Earth, and you wouldn't expect it anywhere near close to the surface. However, we know from meteorites found on Earth that iridium is abundant in meteorites around the solar system, and we suspect that this is true for asteroids and comets as well. So iridium here is a strong evidence of the impact. Not only was it found in only a few sites, but it was found everywhere on Earth, which is consistent with a large impact that was spread all over the Earth. So iridium, very rare on surface rock, but found in meteorites. Now, the people who proposed that in the early 1980s, Luis and Walter Alvarez, found this layer of iridium laid down 65 million years ago, which is fairly rare, and is consistent with an impact that laid out a lot of deposits all over the planet. So the picture that we have currently starts like this. We have a comet or an asteroid about 10 kilometers in diameter that approaches the Earth. And in this picture, it comes from the southern part of the Gulf of Mexico. It is going to impact the upper part of the Yucatan Peninsula in the southern part of the Gulf. Now, at this point in history, this picture is not quite right. The shelf, the continental shelf area, as well as the peninsula, would not have the following picture. Wouldn't look quite like this. But if we follow along in this artist rendition, we expect that impact happen in the North Peninsula, close to the city of Merida. And this caused not just a massive explosion, but a blast wave and a lot of ejecta that polluted the upper atmosphere and was spread all over the Earth. Now, this impact crater would have been several hundred of kilometers across and probably disrupted a lot of area just below the crust of the Earth. Now, you will have a series of concentric rings spraying around, and the reason why we believe this crater must exist is because we can actually see it. So this is going to be a gravitational map of the area around Yucatan, and we see a series of concentric rings. This is all buried below a layer of limestone, but the time of formation is roughly consistent with the time in which the dinosaurs disappeared. So this event is known as the Chicxulub event, and this crater is known as the Chicxulub crater, just named after a town in the northern part of the Yucatan Peninsula. An iridium-rich sediment layer and an impact crater on the Mexican coast shows that we had a massive impact that occurred roughly at the time the dinosaurs disappeared, the KT event. Now, we have reasons to believe, and it would be a reasonable thing, whether such danger or such type of event will happen in the past. So we have to learn how to evaluate the threat and really assess critically what media sources warned us as being a likely event, either it be from movies or from other sources. So this is what we know so far. Asteroids and comets have hit the Earth, and it's reasonable to expect that it will happen again. So major impacts is just a matter of time. the question is not whether it will happen or not, but when. Now, major impacts are very rare compared to smaller impacts, and it's going to be the major impacts that are going to have major damage, not just to human civilization, but also the biosphere as well. So, based upon the record, we expect extinction level events, impacts that are large enough to cause massive extinction, not just in a given region on Earth, but all over the planet, and that this happens at the rate of millions of years. Now, things that cause major damage can happen much more often, like tens of hundreds of years, but such major damage would be confined either to a continent or just a country in terms of area. Now, what are the stocks of this actually happening? The way that you assess these odds is doing a survey of how many objects are there out there in space and how often they should cross the Earth, and also the geologic record. So, for instance, there is 1 in 100 million chance that an asteroid impact cause global disaster in any given year. We expect that you have 1 out of 95 million chance of dying from a venomous snake or a lizard bite in any given year based upon statistics of mortality in the United States. We expect that the odds of dying from a lightning strike in any given year is going to be 1 in 4 million. And 1 in 3 million chance of winning the lotto, say the Georgia lotto, for a 2-draw slip. There are other statistics. For instance, there's 1 in a 2 million chance of drawing a royal flush in spades in a 5-card poker draw. There is 1 in 100,000 odds of an asteroid impact cause regional disaster in any given year. There's 1 in 91,000 odds of dying in a fire in any given year. And there's 1 in 500 odds of having triplets if you give Earth. So, based upon what we know is rather seldom events, we know that the chances of us dying from an asteroid impact is rather seldom compared to other things that we have much more direct experience. And just to round this up, there's 1 in a 6 chance of having a sunny day in Seattle. The following is several footages taken by various cameras over Utah on November of 2009. And this is going to be a slow motion over there. What has happened in recent years is that with the proliferation of cameras, it is possible now to record major fireballs. Chances are that some of these fireballs actually had material that reached the ground. Because of all this footage that is available to us, it is possible, for instance, to track the position and the final landing site of any debris that has reached the ground. But it has also caused a bit of a media panic because this gives the impression there are far more of such events compared to the past. We expect that there are several thousand tons of material that rain from space and over a single day, so there's no particular reason why we should believe, for instance, that the Earth is suffering far more impacts of such bolides as we normally would. In this diagram, what we're showing is the typical size of an impactor size, okay, versus how often we expect those impacts to happen. Now, on every given hour, we have at least 1 or 2 events of an object the size of 1 meter to impact the Earth. Over a single day, you have probably tens of thousands of tons being deposited all over the Earth. So these are not really objects the size of concern because they don't reach the surface. Now, every year, we begin to see objects which are about 10 meters in size. And those are big enough that we start to see explosions or a small crater and debris reaching the surface of the Earth. Once every millennium or so, we expect to see impacts that would be the source of tsunamis and widespread devastation over a continent, and even some climate change based upon debris that's ejected into the upper atmosphere. Now, every million to every 100 million years, we see objects that are greater than 10 kilometers, and such an event will cause mass havoc and disruption of the ecosystem, not just in a given region, but everywhere on the planet. So impacts will certainly occur in the future. As a matter of fact, they're probably happening now. But we have only a chance of major impacts in our lifetimes, which is rather small. The effects of such things would be devastating, but they are rather small compared to other things in our daily life that we can worry about. So, is there an asteroid with our name on it? Well, there are thousands of what's called near-Earth asteroids, and the reason why they're called that is because they actually cross our orbit or they come close enough to Earth. We have not seen one that we know for certain that will collide with us yet, but there are a few that have made the news in recent times. So for instance, we have asteroid Apophis. This is a near-Earth asteroid, and this is a picture showing made by a telescope that's tracking the asteroid in one of its closest events. And notice that the stars in the background are rather smeared as it follows the asteroid. This object is 250 meters wide, big enough to cause massive disruption at the level of a country and maybe cause some climate change as well. So in April of 2029, we know they will pass very close to the Earth. We don't expect at all to impact. They will come within 18,000 miles. Now in the year 2036, it will pass closer still. Now there's some uncertainty here as to how close it will pass, because in 2029 it will pass close enough to the Earth that the Earth's gravity would change the orbit substantially. So this is an object that we will have to track very closely so that we know whether by year 2036 it might be a source of concern. However, people who do explore the dynamics of such an asteroids know that there is a very narrow window, spatial window, that it will have to cross before we would know whether it would be a source of concern in 2036. Currently, NASA puts the chances of such a collision in 2036 as 1.25 million, which is a substantial thing, but is not a huge set of chances. However, this hasn't stopped the Russian Space Agency from proposing missions to change the orbit of Apophis so that it will not cause impact here on Earth. So if we were to do such a thing, if we were to discover an asteroid that was coming close or for certain will come and impact the Earth, we will have to understand how to control it. So unlike the movie Armageddon and other popular ideas, if you were to break an asteroid, say by detonating a nuclear weapon in it, it will just produce a lot of little asteroids that would impact and cause destruction on Earth still. So one thing that you want to do is not to break it up, but actually change whatever it is, however big it is, its orbit, so that it will not affect us. So the bigger concern would be if you had a comet, and a comet can be harder to detect ahead of time with enough warning for us to actually disrupt it. So really comets can be a bigger source of concern than, say, asteroids. So we estimate that there are about 1,100 near-Earth asteroids larger than 1 kilometer, and those are serious things to consider. And there might be more than 1 million asteroids out there that are larger than 40 kilometers in diameter, meters in diameter, and they will make it to the Earth's surface. So it is worthwhile to look for the largest of these objects and see how many there are there and see what orbits they have. So for instance, this is an asteroid called 2010 AB78, and this was discovered recently in 2010 by the Wide Field Infrared Satellite Explorer. So this infrared telescope can actually help us detect rather smaller objects or objects that are too dark to see in the visible, but we can see the thermal signature of these objects. So this suggests that the fact that the Wide Field Infrared Explorer detected this object and our visual detectors haven't suggests that there may indeed be far more near-Earth asteroids that haven't been detected. So we're still trying to understand the statistics of collisions from asteroids. Now, other planets can also affect the impact rates and life on Earth. Okay. In this diagram, what we're showing is an autoscale image of the solar system, and Jovian planets are going to be far more massive than the terrestrial planets, and because they are far more massive, they can actually disrupt many more asteroids and comets from a distance. So we know, based upon our studies, that indeed Jupiter and perhaps sometimes Saturn and the smaller Jovian planets, Uranus and Neptune, can disrupt the orbits of these objects, and sometimes they can be rather unpredictable. So, Jovian planets, by their gravitational effect, already determine where asteroids and comets are today. Some asteroids are in their orbits because they do not resonate, don't have an orbital resonance with Jupiter. So, everything that is in resonance will have been cleared by Jupiter as well. Uh, Other comets were produced by having the Jovian planets eject them far away from the inner part of the solar system. So it may be that as a comet comes in and affects or has a chance of reaching the Earth, it may be disrupted in this orbit by Jupiter in such a way so that far more comets are um, ejected from the inner part of the solar system before they are strike a planet. Or maybe sometimes Jupiter and other objects can actually slingshot comets directly to us. In this animation, what we're showing that with the particular configuration of a comet and Jupiter, how it can be altered so that a comet is eliminated essentially from the solar system. Here we see that the gravitational influence of Jupiter is such so that that comet, which originally was in a stable orbit, has been led to crash into the Sun. This is what's called a sungrazer comet. This is an image taken by the Solar and Heliospheric Observatory, where comets, here's a comet that's falling directly into the Sun. And some of these comets are ejected into the Sun because Jupiter has directed them in that particular direction. So we see several of these comets throughout a given year, and this is an example of the effect that Jupiter can have on comets. One question would be whether Jupiter was necessary for life on Earth, because the more collisions happen, the less likely is it for life to last long on a given planet. So impacts, rather large impacts, can extinguish life, and it would be good to have something that would reduce impacts here on Earth. But were they necessary for life as we know it? Well, in terms of being able to deliver matter and water on the surface of a planet so that life can thrive. So the jury's still out on that. How much do the Jovian planets help avoid impacts or help direct impacts so that life could exist on Earth in the first place? So what have we learned so far? We have indeed witnessed a major impact. This is not a theoretical possibility, but something that happens often enough in our solar system. Aside from comets' impacts on, say, the Sun, or, say, asteroids between asteroids, we had a major event that happened in 1994 where a rather large comet, Schumacher-Levy 9, impacted Jupiter. This comet had fragmented into many individual nuclei or parts of the comet nucleus, so there were a string of impacts that left Jupiter atmosphere scarred for months. And this is probably an example of something that happens in the regular basis, and impacts are not limited to the distant past of the solar system. Did an impact kill the dinosaurs? And it is most likely yes, it is something that's still being discussed. We're not certain whether an impact was the sole cause, but a major impact clearly coincided around the time of mass extinctions, when the dinosaurs died out, which is about 65 billion years ago. There was evidence from sediments and in the layers of the geologic record that an impact crater was about the right age when found near the coast of Mexico. How likely is these things to happen? Well, impacts certainly pose a threat, though the probability of a major impact in our lifetimes is rather slow. we expect that small events happen on a regular basis in rather short timelines, but we expect very massive events capable of massive devastation to happen in very long periods of time. Nevertheless, the chances of such an event happening within our lifetime are real, though rather small. We know that other planets, because of their gravity, affect the impact rates. Asteroids and comets have always been linked some way to the gravitational influences of Jupiter. It could be that Jupiter is still in the process of clearing the solar system from very eccentric objects like asteroids and comets, and that is part of the reason why we don't see as many impacts as we could. And this gravitational influence have shaped the asteroid belt and the Kuiper belt and the Oort cloud, those clouds of comets that extend many tens to hundreds of AUs away from the inner part of the solar system. And those Yogian planets still help determine when an object is flown our way. This concludes today's presentation, and I thank you for listening.